So today we have Chiara Braidotti, who's a postdoc at the University of Glasgow. And this is a slightly different talk from some of the ones we've had recently, in that this will be involving superfluids of light. So I'm quite excited to hear what they've been up to. So I'll let you take it away.
Okay, thank you. Thank you very much also for this invitation. So I'm going to present you the recent measurement we performed of Penrose superradiance measurement. And this research project has been, has been going on for several years. And these are the people that were involved that I want to thank. So let's start. I hope you should see me changing slides. So let's start by introducing the motivation behind this research. So you know that there are some experiments, especially those related to the field of gravitational physics, that aim at investigating effects that need the technology that nowadays we do not currently have. So in 1981, Bill Unruh proposed a way to investigate these phenomena by extrapolating them from the gravitational context. So he proposed an experiment to test Hawking radiation through an hydrodynamic experiment producing a dumb hole. So, and this idea, this proposal that he did started the so-called field of analog gravity. So there is a small sketch of what he was proposing here. So yeah, the water flow and fish that were actually screaming, but the flow was going faster than the speed of sound. And so if they were down the waterfall, their sound could not reach the upper part. And this was, the analogy. So he had an horizon, which was where the water flow was. So he was doing this parallelism between a dumb hole and an actual black hole. And so there are many effects in that, from this starting point has been trying to be investigated. And here I just report a few examples and a few of the fields that are involved. So it's not only hydrodynamics, but actually also optics and fiber optics, as well as superfluids like Bose-Einstein condensates and this kind of setups. And there are many effects. So there is radiation, there is superradiance, which I'm gonna talk to you about today, but there is also false vacuum decay, boson stars, and Unruh effect, and many others. So as I was telling you today, my aim is to describe you superradiance in the frame of nonlinear optics. So let's get into let's start. So in 1969, Roger Penrose proposed superradiance as the way for an alien society, actually, to extract energy from rotating black holes. So the alien society, in his idea, could drop an object inside the ergosphere, which is the pink, area. And we know that in the ergosphere, the object can have a negative energy. So if the object inside the ergo region splits into two parts, and one of the parts falls into the black hole, the other part can be retrieved with more energy than the original object, because it has lost a negative energy. So a similar but as well different effect of amplification was proposed for waves in the same years in a different context, which is from Zel'dovich in 1971. And he adapted this Penrose formalism to waves with an angular momentum. So he noted that for an observer at infinity, so an observer at infinity can view actually any part of the incident co-rotating wave that becomes trapped inside the ergo region. Sorry, I had a video. Okay. So that becomes trapped inside the ergo region as having a negative energy. So in this way, the counterpart From the point of view of the rotating object, the OEM wave is rotationally Doppler shifted, which means that the frequency of the incoming wave changes depending on the frequency of rotation of the object. So we can see this here. So this is like a metallic cylinder that is rotating, and we are Doppler shifting the frequency of the wave with OEM. So when, as you can see, we can see the wave that changes rotation versus, and that means that the object has started rotating faster than the rotation of the wave. So in this way, we can have frequencies that are Doppler shifted that are negative. Let's say in this way, the reflective wave has more energy with the Penrose effect for a black hole. So let's say that in the years, so a bit of history, who gave the name to this was actually Misner. So he found out this parallelism between Zel'dovich and Penrose and proposed superradiance as a name for it. With Zel'dovich, let's say there is this Zel'dovich-Misner condition, so omega minus m capital omega, whereas small omega is the frequency of the incoming wave, m is the angular momentum of the wave, and omega is big capital omega is the rotation of the rotation frequency of the object. So in this way, we can see that it can become negative if capital omega is larger than the small omega. So from this, so this phenomenon is very difficult to be very high frequency, and it's very difficult to spin objects that fast. So there is I will show you later a proposal to how to try to, let's say, overcome this technological difficulty. But at the moment, let's stay with this optics, but actually there is a previous experiment that has been done also with water waves. So they actually had a water vortex, and they were sending in modes, and they were seeing their amplification. So this is the paper I'm talking about. I'm not entering into details, but for completeness, I wanted to tell you this. So now we can move on to our photon fluids. So what is a photon fluid? I start from scratch. I don't know a lot about your background, so I tried to make it a sort of between, let's say, didactical and trying to explain everything, but not too trivial, let's say. So let's start. We have a laser, you'll probably know, we have a laser beam that propagates in a nonlinear medium. And in optics, the equation used to describe this nonlinear regime is the nonlinear Schrödinger equation, which is the one I reported above, where we have, let's say, a 2D NLS with the derivative in the propagation direction, so Z, and a second derivative in the transverse one, which is giving diffraction. Then we have the nonlinear term, which I write here in its most general form, which is a non-local type of nonlinearity. So where R is the response function of the medium and E square is the intensity of the beam entering inside the material. So and that N2 is the nonlinear refractive index. So in this way, what does this mean? It means that when we send in a beam, the intensity of the light hits the material, which responds in a non-local way. So there is a thermal diffusion of the heat, and so different points in the material are affected to what happens in another point. In this sense, it is non-local. So what we want to try to describe how to arrive to our Penrose, let's say, experiment is through a four-wave mixing process. So a four-way mixing process is we send in a pump and a signal beam, and through this pump and signal we generate, let's say, also an idler. Okay, so strictly speaking, two photons combine with a single photon, and this four-way mixing process can produce amplification of the signal and the idler fields only if the two beams are phase matched, and we're going to see what this means later. And I'm going to show you how this four-way mixing process is important for us to describe the Penrose process, and how from this we arrive to the actual fluid, because we do not have the fluid yet, so still in nonlinear optics. So I wanted to tell you this, that in our the material we use, so that the particular thermo-optic medium we are using is a solution composed by methanol and a low concentration of graphene flakes. And the graphene flakes provide the weak absorption of the pump input, and in this way they are enhancing the thermo-optic effect. So the N2 or gamma here, it's the same, let's say, value. It's always the nonlinear refractive index is the focusing, and the non-local response can be, let's say, increase, as I was telling you, it's a diffusion of heat, so it evolves in time, and we can, let's say, doing time resolved measurements, we can actually choose how much non-locality we have and how much non-linearity we have. So if we time gate our measurement, we are able to have a quasi-local non-linearity that can be realized and can be quite small. And this is important in order to see our effect. Let's try to arrive to the photon fluid. So we start from the nonlinear Schrödinger. We can do a Madelung transformation and map the nonlinear Schrödinger equation to two hydrodynamics equations for the intensity, ρ, and the phase of the beam, which is phi in my notation. So if we have a spatially homogeneous photon fluid, so where the background pump is independent of the position, so let's say it's a flat beam, a sound mode of the form of a plane wave with a certain wave vector k that are reported below can be formed, and as the amplitude of the signal and the idler. So the signal and the idler act as a perturbation, and they have a wave vector k that satisfies this dispersion relation with the frequency omega also that satisfies this Bogoliubov relationship. And we can find that it's composed by two terms. So the linear term is the one that gives sound modes, and the quadratic term gives free modes. So I'm plotting here, actually these are measurements that probably Kaylee took as well, with this. So this is the dispersion relation. We see the K and we see the two trends, so the linear part and the quadratic term. And the interesting thing is that the flow, so the velocity field of the flow can be engineered just by choosing the phase of the pump beam. And this can be easily done by the use of instruments like SLMs. So we can actually engineer the flow that we want. And plus we have that the speed of sound, which is, let's say, proportional to this term here, the quadratic term is proportional to C of S, is dependent on the nonlinear refractive index variation inside the material. So we can choose also that. So by choosing the intensity or by changing the nonlinearity. So it's a very versatile setup in this sense. There are also other ways, let's say, to find the Bogoliubov dispersion. I wanted to report this, which is actually very straightforward to get it in this way. So as you see, they have a flat background, which is the blue part here, and they inject a beam that splits into components. And these are the two components I'm talking about so the signal and the idler that we will see later. So how do we create now? So I've been talking about an homogeneous background, but to test the Penrose process, we need to create a rotating background, so rotating space-time geometry. So we introduce an inhomogeneity in the pump beam. Inhomogeneities can create an effective curved space-time where the linear elementary excitations can propagate. So by a perturbative analysis of the hydrodynamic equations seen previously, so the Euler and the continuity equations for the intensity and the phase of the beam, it is possible to show that they can map to a Klein-Gordon type equation of this kind, and where we can actually write a metric for our perturbation. So it's like the pump, it's creating a curved space-time on top of which the signal and the idler, acting as modes on top of this curved space-time, behave and evolve. So I remember you that the speed of sound is proportional to the refractive index variation, and when it becomes equal to the flow speed, which on the other end is the phase derivative of our beam, we have the presence of an ergo region. So what is important for our analogy is the existence of an ergo region and a way to trap the negative energy modes. So I was saying that at the beginning that we have these two modes, a positive, let's say positive frequency mode and a negative frequency mode. And we have to trap the negative frequency in order to amplify the positive one. So what's important is to have this ergo region where they can split and where the negative energy mode, let's say, can acquire its negativity, okay? And this can allow to extract energy and amplify the positive energy one, which is the key ingredient for the Penrose superradiance. And then we have to have a sort of horizon in the sense that we have to prevent the modes to mix again at infinity. Otherwise, the whole energy, let's say, account is lost because we are mixing them again, which is the role of the event horizons in black holes. I've reported here another experiment that shows how that we can create actually a flow, and we can measure both the flow and the sound of the modes. So now we want to see how we should engines in order to get an amplification. So what is yes, so we need to find a geometry. So we need an appropriate background in order to have the trapping of the negative energy mode, and this can be done by the self-trapping of a polarity in the PAM, orbital angular momentum, and there is this vortex that is propagates non-linearly, and the balancing between diffraction and self-defocusing makes it propagate in a stable way. Then the fact that the material is also slightly non-local adds the stability of the whole process of the propagation of the pump. So let's look at this slightly mathematically now. So we go back from the photon fluid to the full description in optics, and I've reported here the two equations for the evolution of the signal and the idler beam on top of the pump beam, which is E0 here, and E pump on top. And we are looking for a geometry where the positive frequency modes are amplified and the negative frequency modes are trapped. So the Bogoliubov excitation here is formed by both the signal and the idler that behave as a unique mode that then gets split into the two components. And the strength of these results is that it relies on the validity validity beyond the acoustic approximations. So it's not only valid when we are in the, let's say, linear part of the dispersion regime that I was showing you before, but also when we are in the quadratic part. And so on the whole Bogoliubov spectrum, the price that we have to pay in order to have this, let's say, validity beyond the acoustic approximation is that we have to measure the negative energy modes in order to get to balance the energies. So that is the price. We always have to keep track of what's happening to the negative energy mode. We cannot lose it. So what we did, let's look at the geometry we used. So we have, if you look at the drawing, we have this pump, which has an OEM. So it has a vortex at the center with a certain OEM L, and it has an ergo region. Okay, then on top of it, we inject an input signal. So here they're drawn in different colors, but actually they have the same wavelength inside the medium. The input signal is again a vortex, slightly wider and with a different OEM, generally independent beams. And they enter together inside the material, and especially the signal is focused onto the pump core. So it has to go and scatter off the pump core. Let's say the assumption here is that the pump has a fixed evolution, so it's not changing to the vortex inside it, it's not changing much, and that the linear is a very weak beam, such that it's just a linear perturbation on top of it. So what we want to see is that in the interaction of the pump with the signal, so of the signal with the pump core, we generate an idler, and especially the idler is what in our description acts as the negative frequency mode. So it's the one that has to become trapped inside the vortex core, inside the sort of horizon. Okay, so inside the ergo region for sure. So what we expect to see at the end is that we will have an amplified output signal that is outside the pump core, and then we have an idler instead that is trapped inside. So they have to have a definite OEM, which is given by the 4-wave mixing process, and they have to be located in different regions. So wait a second. Okay. So by solving the two equations, sorry, that I reported again here for these two, for the two beams, we can actually find a mathematical expression to the wave vector shifts. These I call them wave vector shifts since they're shifts with the nonlinear shifts with respect to the pump wave vector. Delta Ks is the one for the signal and is formed by two components. Let's look at the first one, which is the penetration is given by this gamma coefficient. That is the penetration of the signal inside the pump core. And the other one, so delta Ki, is the one for the idler, and is proportional to this lambda PQ, which are the eigenvalues of the guided mode. So what I'm talking about here. So we have these, if you look at the green picture, you have, that's the pump, okay? So the pump has these, it's like a plateau, and on top of the, inside the plateau, there is this vortex. So the vortex creates a decrease of the intensity, and the decrease of intensity gives a variation of the refractive index that it's acting like a waveguide. So what happens is that we can compute by these lambda eigenvalues the modes that are inside the waveguide created by the pump beam. And that waveguide is what's acting as the sort of event horizon. So it's if we manage to couple the idler inside that waveguide, that is what it stays trapped inside it. Of course, it stays trapped if the eigenvalue is larger than 0. And we're going to see that the idler mode being the one having the negative energy. So let's look at this. Yes, of course, we have to satisfy phase matching condition, otherwise this doesn't work. So the phase matching condition that we find here is that the sum of the two wave vector shifts has to be larger than 0, and this guarantees both that the idler is excited and is trapped, and that we have an amplification of the signal beam. So let's look at the frequencies now. There is a possibility to directly map the wave vector shift into the frequency. So as you can see from this minus c over n0, and 0 is the refractive index of the material, times delta k. So if delta k, we were saying for the phase matching condition has to be positive, means that the energy shift is negative. But what is this frequency shift? This frequency shift is the one of the complete Bogoliubov of mode. So it's composed by the sum of the frequency shift of the signal and that of the idler. And if we look at it mathematically, we can see that we can map this relationship to the Zel'dovich-Misner condition. So the two of them gives this Doppler shifted condition that is proportional to the difference in OAM of the signal, which is N, and the pump, which is L. Omega here is the rotation of the pump, and capital omega, and small omega is the frequency of the mode. So given by the half frequency, let's say average frequency of the signal and the idler. And if you see it, what comes from this, it's that since lambda had to be positive, it means that the frequency of the idler has to be negative. So he's the one acting as the negative energy mode. Plus what we have to satisfy, the condition we have to satisfy in order to have the phase matching is that the difference in OAM has to be larger than 0, which means that the OAM of the signal has to be larger than the OAM of the pump in order to excite the process. So let's look. So these are the three conditions. I just reported them to have a summary here. But let's move on. So what we used to say, the tool that we used to say that we have superradiance is this nether conservation. So what happens is that we have to quantify the reflectivity. So in order to say that we have amplification, we have to have a reflectivity of the mode from the interaction with the vortex, so with the analog black hole, that has to be greater than 1. If the reflectivity is larger than 1, then we have gain in energy. So how do we define these reflection and transmission coefficients? So we see that this system of coupled equations satisfy this conservation of the charge, where we can write the current J0 as the difference in intensity of the signal and the idler. And so once again, you see that the idler one is the one where the energy balance is negative. And so the reflectivity is let's say the integral from outside the ergo region, so the region of scattering, and the transmission is what enters inside. Since the sum of the two has to be balanced, if the transmission goes negative, it means that we have a trapped idler inside, and the reflectivity goes positive outside, because outside we have only the signal, basically. So these are simulations to show you what's happening. So what we inject, we have a pump OAM, which is a pump OAM with OAM 1, and the signal with OAM 2. So in the first row, we are satisfying the N-L condition. While in the second row, we are not, since the signal is counter-rotating with respect to the pump beam. So I reported the current, and we see that it goes negative near the vortex core, which is near 0, in the case of superradiance, and so in the top row, and it doesn't go negative in the bottom row, where we are not satisfying the phase matching conditions. And we can also calculate the reflectivity, and we see that we have an amplification in the first case of the 20%, and we do not have an amplification in the second case. So what we did was we tried to reproduce experimentally these results. do this. So we took, as I was telling you, a solution of graphene nanoflakes, dissolved in methanol, and the graphene, as I was telling you, provides this absorption and it enhances the nonlinear refractive index. So we injected this, the pump beam, which is shown here, and a signal that also I report here is a case for pump OEM equal 1 and signal OEM equal 2 inside the nonlinear medium. And then through a technique which is called digital orography, we are able to extract, so to collect both the intensity and the phases of the beam at the outside of at the exit phase of the sample. And in this way, we can, through an OEM decomposition, we are actually able to see which OEMs are present inside the beam to reconstruct what's happening. So these are linear measurements. So I was telling you OEM pump L equal 1 and signal N equal 2, and the second case N equal -1. So the first case we should have an amplification. In the second case we shouldn't. So we expect an idler mode inside the core if we excite the superradiance condition with OEM equals 0. So we expect it to appear in 0. And we do not expect it to appear in -1 here. Sorry, this is reversed. No, okay, in 3. Okay, sorry. So these are linear measurements. So when we are all linear, so linear pump and non-linearity of the sample, we shouldn't have the creation of modes, which is what's happening. When we go non-linear, we see that we are creating the idler in 0. But we are not creating an idler at Q equal 3 when we are not in the phase matching conditions. So when we should not have superradiance. So if we want to, we can quantify also the currents and the reflectivity. So these are the currents and the reflectivity in the two cases. The first case, we see that the current goes negative near inside the ergo region if we have superradiance, and the idler beam, which is the one with Q equals 0, is mostly trapped inside the ergo region. It's a bit leaking out, but most of its intensity is trapped. While we can see that in the case of non-superradiance, it's all outside. If you look at the intensity of this beam, this is very, very, very weak. It's a bit there, but very weak with compared to the other one. The color scale doesn't show this one. So you have to trust me. And while the reflectivity, we can also plot that. We see that if we satisfy the conditions, we have that we are able to amplify in, let's say, if M, which is N minus L, is larger than 1. So 1, and also actually also this point is amplified. It's just the resolution doesn't allow it. And we tried the same if we satisfy the phase matching condition. So this shows that we are actually able to amplify the positive energy mode, and that the negative energy mode instead, which is the idler, remains trapped inside the ergo region. So this is a proof that actually we are having a sort of Penrose effect through a nonlinear optics descriptions. All the Bogolyubov modes are linear, and let's say everything should works as it should. Then do I have 5 minutes? Okay. I wanted to tell you also a bit about this Zel'dovich effect. As I was telling you at the beginning, the Zel'dovich effect was introduced by Zel'dovich in 1971. So this is the original Pellic cylinder, so conductive, sorry, that was rotating at the frequency omega, and we have an incoming wave with OAM, which now I call M. And if the two let's say, if the with frequency small omega. So if we have a negative Doppler shift, it was showing that the absorption coefficient of the cylinder switches sign and becomes amplification, in analogy with what was happening with the Penrose process, as I was telling you before. So from the analog, what we have learned is that we want to work in the near field regime. So as I was telling you, we cannot speed the electromagnetic wave frequency away a cylinder with that has a frequency that is larger than that of light. That's very, very, very challenging. So we tried to let's say overcome this issue by proposing to be in the near field regime. And so I show you here, this is a bit of the region of technology where we are. So these are, let's say, spinning particles, dentist reels that have been proposed for this to perform these kind of experiments and further on. And we see that we are, so what we would like to be in the far field. So we have actually a wave that has a definite frequency omega or wavelength lambda that is smaller than the dimension size of the system. We want to be in the pink region here, but technologically we cannot yet arrive there. So what we try to do is to be in the near field regime. So we are taking an object which is actually smaller than the wavelength, and we want to see if we can, let's say, excite the Zel'dovich effect as well. So an experiment of this kind has been realized with sound waves recently, also in Glasgow. So they had a ring of speakers that were creating fictitious, I would say, rotational wave with sound that was going to impact on an absorber, on a rotating absorber. And then behind the absorber, there was a microphone, and the microphone was actually able to detect the amplification of the sound if the, let's say, absorber was rotating faster than the wave, than the wave. So there is a lot of literature about this topic, as you can see. Some, let's say, older, some recent, and with proposals with dentist reels, as I was telling you before. Our proposal is to do this instead of with a cylinder, with a rotating sphere. So the whole idea started from this paper, which is a paper from Schack. And what they were doing was they were creating this sort of OEM beam, magnetic beam, in this case, magnetic field with OEM. And they were using it to spin a particle. And they were trying to spin it so fast that it was breaking. And they were studying at the break of the particle. So we saw this, and we realized that actually it was very similar to what we wanted to do for the Zel'dovich effect. So this is the proposed setup. So we have a superconducting circuit that is all of these chip, we could say, that is formed by 4 microcoils that are linked together by transmission lines. The whole length of the circuit, so of the coils plus the transmission lines, which are very, very long actually, gives the wavelength of a mode that is a magnetic mode inside this circuit. And it's built in a way that the magnetic beam is, the magnetic field is phase shifted between the coils in order to have it rotating in a wavelength, so in a trip around the circuit. So it works in this way. We have this rotating B field inside, while the current is passing inside the transmission line and the whole circuit. So what we do, which is in analogy for what Schack's proposal was doing. So what we do is we put now a sphere inside it, and the sphere is rotating, And we create, of course, the magnetic field is rotating as well, but the sphere is following it with this momentum that follows back. So we have we have a response function from the sphere. So if we do not have the Zel'dovich, we expect the sphere to rotate slower than the magnetic field that is driving it. So you have to imagine sphere now rotating independently from an outside magnetic field, okay? And we probe it with this small circuit, sending onto it a small B field. So now we have that if we do not have the Zel'dovich effect, so if the frequency of the field is larger than the rotation of the sphere, then we have that the M is following B, while if we are in the Zel'dovich effect, the out of phase component switches sign. So because the absorption is switching sign to becoming gain, and hence the M is also preceding, let's say, the B field. How does this happen? So the magnetic momentum that is induced by these eddy currents that are present on the surface of the sphere. And we can actually compute them mathematically. And we see that the magnetic momentum is proportional, let's say, for this alpha coefficient, which is the response function to the magnetic field. And the alpha coefficient is composed by two functions, one that is real and one that is imaginary. The imaginary part gives the absorption, and this is the one that switches if the rotation of the sphere is faster than the one of the field. So we have this omega R, which is the relative frequency, which is the rotation of the field, which is small omega minus the rotation of the sphere. And we can compute the power that is dissipated by the sphere. And you see that it's proportional to this key, and this key function is proportional to alpha. And we see that for the reality value of the response function, we have that it switches sign. So from dissipated power, it becomes gain power. And we can compute this absorption in this way. I'm not entering too much into the details, but if you want, I can tell you later. It was going too long. So by plotting the gain, so this you can see that we have two regions, one that is loss and one that is gain. So the gain is when we have that we are spinning faster than the magnetic field frequency, and loss in all other cases. And this is actually an interesting setup, because it's true that is technologically challenging. The circuit has to be very, very long in order to have like 70 meters long. It's not very small. It has to be superconductive, because we do not have to have loss amplification. So the global losses has to be smaller than the actual amplification of the effect. And of course, it's very difficult to have a large stability of the spinning sphere, but it's something that it could be potentially done if, let's say, we can push the technology. And the nice bit also is that by reducing the temperature of the whole system, it would be possible to make it quantum. So to actually extract quantum, so not to have a probe. So now we are having a probe, so we are sending a magnetic field, and we want to see the amplification of the magnetic field we are sending onto the sphere. But if we lower the temperature enough and increase the frequencies, we could have a regime where we can actually able to, so what was the original Zel'dovich idea, so to extract particles from the vacuum, so the vacuum modes. And this is, of course, if doing the normal
Excellent. Thank you very much for your talk. And if people have questions, just raise your hand and but first I have a question, which is, you just said that you need a 70-meter long circuit, but I missed why it's important to have, why that constraint is necessary.
So the constraint is necessary because you want a certain frequency range. So the problem here is that you have wait, let me try to show you from here. So you want to spin the particle at a certain frequency. So the particle has to be, in order to spin the particle at a certain frequency, you are, as I was showing, the first paper I showed you is a paper where they're actually spinning a sphere and breaking it. So there is a breaking point if you spin too fast. So you have that constraint. So in order to, you have to create a magnetic field that has a frequency that is lower than that.
But is it
and the frequency is
Sorry.
proportional to the, as I was telling you at the beginning here, you see that the frequency is inversely proportional to the length of the circuit.
Right.
So in order to have a smaller frequency, you have to have a very long circuit. And that's the problem.
Right. Okay, I see. Thank you.
So, sorry, is it possible to use just 2 synchronized generators for this?
You're welcome. Yes, it's a bit tricky. Yes, you can use two synchronized generators. The only issue is that we would like to actually see the mode inside the circuit. So if you have just 2 synchronized generators, you do not have a complete mode.
So you want to measure this wave, not to apply it. I see.
Yeah, because to see the amplification, you have to see that in the circuit you have that the current, for example, is amplified. So you need the whole the mode there. I think there is a question.
Yes, Samuli, do you want to unmute?
Yes, thanks. So I wanted to go back to the basics of the photon fluid part, and at least some of the results you were discussing explicitly mentioned this being a superfluid. So I was wondering, how do you characterize the superfluid? Like, how do you know that it's a superfluid? Maybe a very stupid question.
No, it's not. So let's say the basic principle is this. So if you inject a mode inside, for example, if you have a background that is flat and you inject a mode with a certain k vectors, you have to see this splitting, and furthermore you have to see that the two modes have actually a definite velocity, so they cannot propagate randomly. So this is the first one. In our case, we are so the important bit is that the whole process is linear, so we do not have a higher order OEM generation. In this way, we know that the two equations are these two, and if we enter at a small angle, we are actually in the linear part here, and this is sort of course we can also be at the boundary, let's say, but the problem is that if you're focusing too fast, you do not couple with the waveguide because you have a too large angle. So what's necessary, it's it to be a photon fluid in order to have to satisfy these two equations and to create actually the idler mode. If it's not a photon fluid, you cannot have the coupling as well. Does it make sense for you? Yes.
Grigory, you want to ask your question?
Okay, just thank you very much for very interesting talk. Just a small comment, maybe related to history, because you did not mention the name Stravinsky, and this is one of the important steps. Stravinsky, after Zel'dovich, he considered the rotating black hole, and after that, Hawking, he came to Moscow. I think it was 72, something like that, and he realized after that, after his visit, he realized that the method which was made by Zel'dovich and Stravinsky, because Stravinsky applied it to the black hole, it can be applied not only to rotating black hole, but to the stationary black hole. And this gave the famous Hawking radiation. So Zel'dovich was just at the beginning, then the next step is Stravinsky, and after that Hawking. So this is the comment. And also I want to tell to Samuel that if you just have a small cylinder rotating in superfluid in helium-3A, I think you will be able to see this Hawking Zel'dovich, Zel'dovich, Stravinsky, Hawking radiation. Okay, thank you.
If you have, sorry, what?
If you have some small cylinder which is rotating inside the superfluid helium-3. So I think it's a good experiment which can be done.
Yeah, yeah, it's part of one of the papers you were telling me before.
Yes, right. Okay, thank you.
Do you have a follow-on to Lily?
Well, I will just tell Grisha that that Dima is actually designing an experiment of levitating objects in a magnetic field, and I suspect it wouldn't be a massive expansion of that in some future edition to allow rotating the object as well.
Yeah, I think it's more difficult, but yeah, it's something we can think about.
Yeah.